Next, we are looking at the idea of velocity. So velocity, the cousin of speed, has one more dimension to it, that is direction. So it's a rate of change of position with respect to time in a given direction. So thus making it a correct vector quantity. When it comes to dimension, it's the same as that of speed. I'm not going to deal with that now. SI unit, same as speed, meter per second. Direction of velocity is something that we need to consider. I hope you guys have done vector topic. So we have an object, say, moving this way, right? This is the direction of motion. That is the direction of motion. And so the direction of velocity will also be the same. So that would be your direction of velocity. Okay, so done and done. Now types of velocity, uniform velocity. That is, we are covering equal distance in equal interval of time, and the direction also does not change. So simple example is over here, right? That's your uniform velocity. So the equal distance or displacement position that it covers, it's moving away in this case. It's equal for every 1 second for this graph, that is. And you can see the velocity graph also. It's at the bottom, it's constant, right? So how do you map it and all of that? I've gone in detail with speed, so please watch that. How do you tell if it's uniform or not? Actually, let me do this again. So why is that we are telling this is uniform, right? Let's discuss that. I'll take another. So we are looking at uniform velocity. So remember, the direction is also was also in one particular. It was in one particular direction. Movement was in one particular direction. This is to do with direction of. Let me. Not good to write stuff without heading, right? It should make sense. This is to do with topic of direction of velocity. It's always in direction of motion. Again, all of these small things, you might feel it's easy. That's good. It is easy. Point is, when there are too many things, you should not get confused. That's it. Okay, so get this things which are easy. Keep it easy. Get it into your head, and then you'll see the complicated ones later. So uniform velocity, we were at uniform velocity, this thing. Now we are trying to analyze. Okay, we're trying to analyze why is this a uniform scenario. So every, say, 1 second, let's see what is happening. So I'm taking on the projection. Actually, I should be doing this. Technically, I should be doing this. So every 1 second, I'm just marking where the graph is at. So indicating how far the object has moved. Again, remember, this is displacement. Right now. So this is basically the projection. I can even do this. Okay. And then I can talk about, just a second. I can talk about this width, right? So this width, it would be not that big and not that color. Agree? It's this. So now if I happen to copy this and check out everywhere, you can see that the width remains the same. Even here, if I do this, it will remain the same. Sorry, this is not a good situation. I did some. Okay, can you see that? So if I keep doing this, the gap, it will be the same. That's why it's uniform. So every second we can see the same distance is being covered. Again, all of this projection idea and how do you understand all of this? This has to be learned from slopes and all of that. So fundamental basics of all of this are basics of your physics, reading graphs, understanding graphs. When I tell projection onto x-axis, projection of the point onto y-axis, all of this has to be understood very clearly. Graphs are very important. I'm going to discuss everything with graphs. Whenever it's possible, I'm going to draw, I'm going to discuss with graph. So this is an example of uniform velocity. Average velocity, quite simple. I opened the same thing again and again. Where is this? Oh yeah. Next is your average velocity. Okay. So how is average velocity defined as? Actually, we do have the definitions. So uniform velocity, when the object travels same distance in the same time and with no change in direction, then it gives a scenario for uniform velocity. Right? And then you have average velocity. Average velocity Vx of a particle is defined as a particle's displacement divided by the time interval during which the displacement occurred. So let me show it mathematically. So this is how it looks like. Say we're considering a particle moving along the x-axis. So we can define it in this way. So this subscript indicates movement along x-axis. This indicates average. This indicates change along x or change in displacement. This is change in time. So that's that. So that's your average. So basically, whatever change in displacement we are looking at, that value you have to take, and change in time between this time. Whatever change in displacement we see, if I just divide those two, I'll get average velocity. Quite simple, right? We'll be doing numericals, don't worry. That's mathematically, that's how it looks like. And next, the one which is confusing for all, that is instantaneous. The concept of instantaneous, anything instantaneous can be understood with the help of limits and derivatives. I mean, it's just that it's the application of that. So we can't understand all of this without limits and derivative. Instantaneous velocity. So I can define instantaneous velocity. I'm just going to write this as displacement. Let me write it here. Yeah, displacement at t plus h minus displacement at t divided by time. In this case, time would be something like this. And one more main thing is, I don't have space over here. I need to do this. And we have limit h tending to 0. We have seen this in speed as well. So yeah, this comes from the concept of your limits and derivative and first principle. So I can also rewrite all of this in a very simple manner. So limit delta x by delta t as delta t tends to 0. As simple as that. Right? So this is one more way of discussing that. And another way of discussing about instantaneous velocity with graph. So graph, we have the following, and we have, say the object has something like this. The displacement time graph looks like this. Now, if I want to know a displacement at a particular point, right? So what I have to do is, first thing is, I need to know the time, initial time and the final time, and see what is the displacement at that moment of time and this moment of time. And my funda is that this gap, this difference in time, this represents difference in time. This has to tend towards 0. Means these 2 points have to come close to one another. They have to come close. Okay. So whatever value we get, the slope that we get post this. So remember, slope of this is nothing but, one more thing is, slope of distance and time graph, the slope will give you velocity, right? So displacement by time gives you velocity. So slope, all this concept has to be very clear. Again, I repeatedly I'm telling this. So without that, it will not make sense. All of this will not make sense. Okay. So graphically, it looks like this. So when we have delta t tending to 0, that's when we get instantaneous correct velocity. So let me show it with a small animation which makes it very clear. So please observe the x and y axis first. Right? Look at the x and y axis. It's time and position. Now, the white line that you're seeing on the screen, that is connecting the 2 points, the slope of that will give you the velocity between average velocity now, as of now. It's the average velocity between from the time 3 to 7.5 seconds. And now the animation, it's decreasing the time difference. So still all of this is average scenario. This is average velocity. This is average velocity between 3 and 6. That is difference of 3. As you can see, we're getting closer and closer. Observe dt at the top. It's 0.969. And as and when we do this is also a very big value. dt value over here is also a very big value. So this is still not instantaneous, but we're getting close to it. And so on and so forth. So this can be considered to be instantaneous. Okay, this is a clear example of instantaneous velocity. So this is the funda. So the same idea is used to discuss limits and derivatives. So that will make things very clear. Connecting that and this, that is. So we just discussed about velocity. It is nothing but your change in position with respect to time. With in what direction, that is also a factor. It is a vector quantity and the direction is same as the direction of the motion. And when it comes to types of velocity, you have uniform, non-uniform, average, instantaneous, so on and so forth. So uniform velocity deals with traveling same distance in same time with no change in direction. That's important. And you have all of these graphs that we discussed. Then we looked at average velocity. Average velocity is to do with change in displacement by change in time. And we kept seeing that over here. So all of this is an example of average velocity. Okay. Then the main thing, the instantaneous scenario. So instantaneous. Oh yeah, average velocity, you guys already did. That's the math is the definition. That's it. I can't tell more than that. Instantaneous speed is velocity at a particular time. So this keeps happening. The time difference between the 2 points that we are considering, it keeps reducing. It will keep tending to 0. So that gives us instantaneous scenario. Okay, so yeah, if you want to write something, you can do so now. So for uniform velocity, this is the graph. This is the math. This is to do with instantaneous velocity. The math, that is. And this is the graph.